Section 4.3 Similarity. The key idea of this section is similarity. The similarity is about the ratio between two square matrices of the same size. And then we'll use this to take the ratio of two matrices. They are used to represent the same linear operator on the different bases of a vector space. Here is the definition. Suppose we have two n by n matrices A and B. We say B is similar to A if B equal to the inverse of S times A times S. From this equation, we can say S should have inverse. And then S should be a n by n matrix. So this is the definition for B is similar to A. The first question is B is similar to itself? The answer is yes. Why? For that, you can just look at the definition. So the left side is B. Then here in the middle is B. Now how to get this? Now that's simple. We just take S equal to n by n identity matrix I. Then this equation is satisfied. The second question is this. If B is similar to A, can we get A is similar to B? The answer is yes. To say this, we started from this equation because it said B is similar to A, so that we can find a non-singular matrix S such that B equal to S inverse times A times S. From this equation, we can take product. From the right side, we multiply it by the inverse of S. And then from the left side, we multiply the S. In such a way, we can get A equal to the inverse of S, take inverse, then times B times S inverse. So look at the definition, we can say this is a matrix inverse, then this is the matrix. So from here we can get A is also similar to B. Because this, we say A and B are similar each other. Let's take a look at the definition of this equation again. What we need is a non-singular matrix, then multiplied by A. The matrix and its inverse on each side. So that's the definition. We should have a non-singular matrix S and then the inverse of the same non-singular matrix S. Here is the third equation, the third question. Let's say we have A and B are similar, and B and C are similar. The question is, are A and C similar? The answer is yes. How to do that? Now for that, we can write down A equal to a non-singular matrix to the inverse, and then times B times the matrix. Same thing or similarly for B and C. And then we do the substitution, we can show A should be equal to the inverse of matrix times the C times the matrix. So you can write down the detail and just use the definition here. We can show in this case A and C are similar each other. Example 2. We assume A and B are similar. We want to show the transpose of A and the transpose of B are similar. And then for a positive integer k, we look at the power of A, A to the power k and B to the power k, they are similar to each other. How to prove this? Just use the definition. Let's consider the first part. We want to show the transpose of A and the transpose of B are the same. Where we start? We start the assumption A and B are similar, so that based on definition, we can have a non-singular matrix S such that B equal to the inverse of S times A times S. Then start from this equation, both sides we take transpose. So the left side take transpose, we get the transpose of B. Then same as the right side take transpose. Now this is the transpose of a product. How to calculate that? Now based on our previous result, that's the same as we take the transpose from the right side first. So that's the S transpose. And then the middle A take transpose. Then the left one take transpose. Also, we need to recall a result in previous chapter. The inverse of S take transpose is the same as we take the transpose first and then take inverse. Now we can say here we have a matrix S transpose and its inverse. So these two matrices are inverse each other. So based on the definition, we can say the transpose of A and the transpose of B are similar by the definition. To prove the second part, we still use the assumption or use the equation B equal to the inverse of S times A times S. We consider B to the power k. That is the same as B times B times B times B. How many b's here? K. K b's here. And then each one we substitute B by S inverse times A times S. So we got one here, the second here, the third one to the nth B. Then we take a look. S inverse, so that's we keep it here. Then here we have S times its inverse, so the product is equal to the identity matrix I. And then we can here the large group, and then continue this way. We can say the middle part is just the A times A times A times A. How many A's? K. K A's. So that is K to the A to the power K. In this way, we can say the inverse of S times A to the power K times S is the same as B to the power K. Then from the definition of similarity, we say B to the power K and A to the power K are similar each other. Example 3. Again, assume A and B are similar. Also, we assume A is non-singular. We want to show B is also non-singular. Because both are non-singular, then we consider their inverse. And we want to show the inverse of A and the inverse of B, they are also similar. Let's look at the first part. We want to show B is non-singular. How to do that? We start from the assumption. The assumption is A and B are similar, so that there is a matrix S, which is non-singular, and B equal to the inverse of S times A times S. Then both sides we take the determinant. So the left side we got the determinant of B. Then right side is the determinant of S inverse times A times S. Now this is the determinant of a product. To evaluate that, that's the same as each one we take the determinant, because each one is a n by n matrix. So we got the determinant of S inverse times the determinant of A times the determinant of S. And then determinant of S inverse is the same as we take a determinant first, then take the negative power, or determinant of S inverse is the same as the reciprocal of determinant S. Then we can say this is a number, this large number, both here is related to determinant S. This is reciprocal, that's just the number, so their product is 1. We got this equal to the determinant A. Determinant A is not 0. Why? Because we assume A is non-singular, so that the determinant of B is non-zero. Determinant of B is non-zero, that means B is non-singular. So we prove the first part. To prove the second part, we still use this equation, B equal to S inverse times A times S. This time, because we want to have A inverse, B inverse, so that what we do is both sides we take the inverse. Take inverse of the left side, we get B inverse, and then the right side the inverse. Here is the inverse of a product of 3 matrices. How to do that? This should be similar to we take transpose. So we start from the right side here. The right side is S. S take inverse, and then A take inverse. Then the left one, S inverse take inverse. But S inverse then inverse, that's the same as S. From this, we can say this side is A inverse multiplied by, from the left is the matrix S inverse, and the right side is S. So the same matrix, one take inverse, the other is the matrix, so that based on the definition of similarity, we can say A inverse and B inverse, they are similar. So we prove the third part. Sorry, the second part. Let's look at theorem 4.3.1. Here we assume V is a vector space of dimension n. When we have this assumption, then we can say it has a base. The base should have n linearly independent vectors. Here we assume v1, v2 to vn is the ordered base of v. And also we can find another ordered base. This time we call this is w1, w2 to wn. Then we assume S is a transition matrix representing the change from F to E. In this way, we got W1, W2 to Wn is the same as V1, V2 to Vn, then multiplied by S. S here is a n by n matrix. Why? Because V1, V2 to Vn is an ordered base for the vector, so that each W can be written as a linear combination of V1, V2 to Vn. So in this way, we can say V1 is the same as a linear combination of V1, V2 to Vn. That means we can have this one multiplied by the matrix S is the first column. Same thing, W2 equal to V1, V2 to Vn times the multiplied by the second column of S. Then Wn equal to the linear combination of V1, V2 to Vn. Now in this case, that's the multiplied the last column of S. So from this we can say S should have n columns. And on the other hand, we can also write V1 as a linear combination of W1, W2 to Wn. How to do that? Now actually we can, both sides we can multiply by the inverse of S. So in that way we can get W1, W2 to Wn is same as, V1, V2 to Vn equal to W1, W2 to Wn times the inverse of S. Now assume L is a linear operator on V, or a linear transformation from V to itself. If A is the matrix representing L respect to the base E, so what's the base E? That's V1, V2 to Vn. And then we assume B is the matrix representing L with respect to the base F. So that's respect to W1, W2, Wn. Then the conclusion is A and B are similar. And more precisely, we can write it down B equal to S inverse times A times S. Now what is S? S is a transition matrix. Here we give a proof. This proof is different from the proof in the textbook. Recall, A is assumed to be the matrix representing L with respect to the base E, so that we can write down LV1 is equal to V1, V2 to the Vn, the linear combination. So in that way, that's actually LV1 equal to V1, V2 to Vn times the first column of A. Same thing, LV2 equal to the linear combination of V1 to Vn, then that's the times the second column. Continue this way, we can say the result after the transformation, we can get LV1, LV2 to LVn equal to V1, V2 to Vn times A. And then similarly, B is a matrix representing L with respect to the base F, so that we can get LW1, LW2 to LWn equal to W1, W2 to Wn, then multiplied by the matrix B. B is the representing matrix. By the assumption we have the transition matrix S, which means W1, W2 to Wn equal to V1, V2 to Vn times S. Now, for this equation, both sides we take the transition or take the linear operator L. Then the left side is LW1, LW2 to the LW2, Wn. The right side take the transformation, we get LV1, LV2 to LVn. Then, for this equation, we do the substitution. Now take a look. The left side is the same as the left side of this equation 1. So we substitute this by V1, V2 to Vn, and the second part, so the left side by this one, the right side by this right side, then we get W1, W2 to WB, so that's this part, or the left side equal to this. This one is the left side. And then LV1, LV2 to LVN, we replace by the right side of equation 1. So that's V1, V2 to Vn times A. So that's the first part. And then we have the S at the end. So in this way, we get equation 3. Now the left side of 3 is the same as V1, V2 to Vn times S times B. Why? Because we had the assumption, we said S is transition matrix, so actually this is the assumption. So this side we substitute by V1, V2 to S, so we get the left side here equal to this. And then in this way we can say equation 3, the left side is this, so we get that. And then the right side is V1, V2 to Vn times A times S, so we get this. So sorry, no comma there. In this way we get the equation. What does this equation tell us? It tells us we can have V1, V2 to Vn times S times B is the same as V1, V2 to Vn times A times S. Now here, both sides, we have the same item. This is ordered base, so that we can say SB should be the same as AS, because V1, V2 to Vn are linearly independent, so that SB and AS should be the same. They're the same, then we can take the inverse of S, then multiplied by this equation, we get this. And look at the definition, we can say B is the same as the inverse of S times A times S. So in this way, we prove the theorem. Example 4. Here we consider the differential operator D. The V is P3. Recall P3 is the vector space of all polynomials of degree less than 3. Here we have 4 questions. The first question asks us to find the transition matrix from the ordered space 1 x plus 1 x squared minus 1 to the ordered space 1 x x square. Then second, we want to find the matrix A representing D with respect to the order of the base 1xx squared. Then do the similar thing for find a matrix B representing the differential operator D with respect to the base 1x plus 1x squared minus 1. Now, how to say this is a base? Now, to do that, we need just to show these three vectors are linearly independent. The last question is show that B equal to the inverse of S times A times S. Here, for the first part, we can show 1x plus 1 x squared minus 1 equal to 1x x squared, then multiplied by this matrix. Why? You can say this. 1 equal to what? 1 equal to 1 times 1 x times 0 plus x squared times 0. So that's this column. Then look at the x plus 1. X plus 1, we can write it down. That's 1 times 1. Then plus x times x. Then x squared times 0. So that's give us the second column. Then x squared minus 1, that we can write it down as 1 times -1. Then plus 0, x times 0. Then x squared times 1. So in that way, we got the third column. From this, we can say the transition matrix X, the transition matrix XS is equal to this matrix here. So that's S. Then we look at the matrix A, which is represent the linear operator with respect to the order of the base 1x x squared. So to do that, just like what we did in section 4.2, we take a derivative of 1x x squared. Now that, of course, the derivative of 1 is 0. Derivative of x is 1. Derivative of x squared is 2x. Now this we can write it down in terms of the base. So this vector is the same as 0 equal to 1 times 0, x times 0 plus x squared times 0. So that's just 0. Then 1 times 1, we got 1. X plus x times 0 got 0. X squared times 0 got 0. So that's just 1. So that's the item here. Then 1 times 0 got 0. X times 2 got 2x. Then x squared times 0 got 0. So in this way, we got the representing matrix A equal to this. So that's A. Then we do the similar thing for the second order of the base. So we take derivative of 1 x plus 1 x squared minus 1. The derivative of 1 again is 0. Derivative of x plus 1, that's equal to 1 plus 0, so that's 1. Then derivative of x squared minus 1 equal to 2x minus 0, so that's 2x. Then this we can write it down as this vector times this matrix. Now for this we can say 1 equal to 0 equal to 1 times 0 plus x plus 1 times 0, x squared minus 1 times 0. So we got the first. Then 1 times 1, we got 1. X plus 1 times 0 got 0. X squared minus 1 times 0 got 0. So that's the one here. The similar thing, 1 times negative 2, we got we got 1 times negative 2, we got negative 2. X plus, then x plus 1 times 2, we got 2x, then plus 2. So got a cancellation, we got this 2x. Then x squared minus 1 times 0. So in this way, we got the 2x. So from this, we can say the representing matrix B is equal to this part. So that's that. Then we want to find the inverse matrix S. So this is the inverse matrix S. We can use elementary row operation. We can find the inverse of S. In this way, the inverse of S is given by this way. Now this one you can easily verify. And then we can take a look. This matrix times A, then times S equal to B. Now this is just do the simple multiplication. You can verify this equation. This equation is actually the conclusion in the last theorem. Example 5 here, we consider linear operator from R3 to R3. And in this case, Lx equal to this matrix times x. We can show this is really a linear operator. And actually, in the first example of section 4.2, we had that kind of example here. The first question, we want to find the transition matrix S from the ordered base. Here, the base has 3 vectors, v1, v2, v3. And then to the standard base e1, e2 to e3. Then the second question is we want to find the matrix A representing L with respect to the standard base e1, e2, e3. The third question is we want to find the matrix B, which represents L with respect to the ordered base V1, V2, V3. First one, transition matrix. So V1 is 1, 2, 3. The component of V1 is 1, 2, 3. So we can say that is precisely 1, 2, 3 here. Because what? Because V1 equal to E1 times 1, that's 1. Then E2 times 2, we got 2 here. E3 times 3, we got a 3. Because E3, the first component of that is 0, 0, 0, 3, so that we got 1, 2, 3 here, that's the V1. Same thing for V2 is the same as 4 times E1, then 5 times E2, 6 times E3. V3 equal to 7 times E1, 8 times E2, 10 times E3, so that we got this is the transition matrix from V1, V2, V3 to the standard base E1, E2, E3. So this is the transition matrix. We can say this matrix S is a 3 by 3 matrix. And also we can show this matrix is non-singular. How? Just take a look at the determinant of this matrix, which means you can use 1 times 5 times 10, then plus 3 times 4 times 8, then plus 2 times 6 times 7, then minus 3 times 5 times 7, minus 2 times 4 times 10, minus 1 times 6 times 8. Now you can find the value here for the determinant of S is non-zero. So this shows here actually S is a non-singular matrix. The second question is ask us to find the matrix A, which represent L with respect to the standard base. Now this matrix is just equal to 1, 2, 3, 4, 5, 6, 7, 8, 9. This is precisely this matrix here. Y equals this. You just plug in, for example, x by e1, then you can get that is the same as L e1 equal to this vector times e1 that gave us 1. And then we can say that gave us, we can get the first column here, the second, and the third use the similar way. Then from here we can find the inverse of S. Earlier we said S is non-singular, and then we can use elementary row operation to find its inverse. The inverse is again by this form, and then we can use the last theorem to find the matrix B. So B equal to the inverse of S, then times A. A is this one, and then times S. So in that way, we can get the matrix B represent the linear operator L with respect to the ordered base V1, V2 to V3.